continuing with section 11.5, the alternating series, we saw an example of how to apply the alternating series test in order to check the convergence of the series. Alternating series are more likely to converge than the positive term series. There is something called absolute convergence. So, an alternating series or a series with some negative and some positive terms has the option to be absolutely convergent or conditionally convergent. What do we mean by that? Let sigma an be a series and then absolute of sigma an another series. Then absolute convergence will happen when we have both of these series are converging. When both of them converge, the one with the alternate or the one with the mixed signs and the one with the all positive terms. So they can both converge, in which case we have absolute convergence. They can both diverge. And the third condition is that one of them converges and one of them doesn't. Can it happen to both? No. The only condition could be that the series with positive and negative terms converges and the series with just the positive term diverges. Then we have conditional convergence. Now let's look at a couple of examples here. First one is summation 1 over n square, n is equal to 1 to infinity. Now this is a series with positive terms, and we note that 1 over n square is a p series and it converges because p is greater than 1, it is equal to 2. Next one, 1 over n, summation 1 over n, this is a harmonic series, so this diverges, and then c here is summation negative 1 to n plus 1 and 1 over n, and we saw this converges, but this is alternate harmonic series because it has positive and negative terms, and we can see from the we actually saw in the first example by applying the alternate series test, this series converges. Then we have absolute convergence test. So first we learned what do we mean by absolute convergence. Now the absolute convergence test is basically that if you are given a series, summation an, and you look at the series summation an with absolute sign, so then if these series is absolute values or all positive values converges, then the original series will also converge. So let's another example here, looking at summation sin n over n cube. Now this series will have some negative terms, but it won't be an alternating series. So we look at the absolute terms of the series or the absolute series, which means all the terms have been made positive. All terms are positive. Then we have summation n is equal to 1 to infinity absolute value of sine n over n cube. Well, we don't need to have the absolute over here because n is starting at 1 and going to infinity, so it will never be negative. So we will never have the negative sign in the denominator. But the numerator, remember the sign stays between -1 and 1. So we have that absolute of sine n is less than or equal to 1, and the hand which is 0 is less than or equal to sine 1, sine n. So that we can compare it with the summation 1 over n cube, because sine of absolute value of sine n will be less than or equal to 1, so that absolute value of sine n over n cube will be less than or equal to 1 over n cube. Now this series summation 1 over n cube converges because it's a p series with n is equal to 3, which is greater than 1. And then we can do the comparison test. We compare it with the sine of n over n cube absolute, and we see that because of the 1 over n cube converging, we will have the absolute value of sine n over n cube will converge by comparison test. Also, this by divergence, by absolute convergence test, now we can say that the summation sine n over n cube will also converge by the absolute convergence test, so that the series sine of n divided by n cube is absolutely convergent. Now note here that this absolute the series test and the absolute convergence test works well for series in negative terms that are not alternating, and typically it is used in combination with another test. Let's now look at some of these examples below. The first one is saying the series summation -1 to n plus 1, 1 over n cube. So we can check the whether it is convergent or not, and then if it is convergent, is it absolutely convergent or conditionally convergent. So the first example, which is sigma 1 -1 raised to n plus 1, 1 over n cube, we can apply the alternating series test, and or we can apply the absolute convergence test. So if I apply the absolute convergence test, the first you can see that the series is just summation 1 over n cube, and this will be the absolute Vn type term. So this is convergent, So which means the series itself converges, and so it is absolutely convergent. Or we can first use the alternating series test, which I have done here. So Bn is 1 over n cube. Bn plus 1 will be 1 over n plus 1 cube. And then Bn is greater than 0, of course, because n is starting at 1 and going to infinity. All terms are greater than 0. And then we have the Bn plus 1, which is 1 over n plus 1 whole cube, will be less than Bn. So the next term is less than the previous term. So it is a decreasing series, and so limit of a sub n will be limit of 1 over n cube, which means which is 0. So all three conditions of the alternative.
I didn't understand that.
All conditions of the alternating series test are confirmed, and so we say that this is convergent. Now, for absolute convergence, we have to again check just the summation 1 cube, 1 over n cube, which we know is convergent. Therefore, series is absolutely convergent. Looking at the next one, which is negative 1 raised to n 1 over square root of n. So now I'm looking at this series. And how can we show that this is convergent or not convergent? We are looking at example 2, summation negative 1 So if we look at the summation absolute of an, this will become summation 1 over square root of n. So this will this is going to be diverging or diverges, because this is a p series. With p equal to 1/2. So this it diverges. But if we are going to look at the original one. So we have Bn is equal to 1 over square root of n, and Bn plus 1 is equal to 1 over square root of n plus 1. Now Bn is first condition. Bn is always greater than 0, which is true. Second condition, that Bn plus 1 is greater than Bn, is less than or equal to Bn. Is that true? Well, we have that n plus 1 is going to be bigger than n, and square root of n plus 1 will be bigger than square root of n, and then 1 over square root of n plus 1 is less than or equal to 1 over square root of n. So this shows that bn plus 1 is less than or equal to bn. So second condition is also satisfied. And the last condition, third condition, limit as n goes to infinity of bn, which is 1 over square root of n. And this limit is 0. So we can say that this converges. This converges. Therefore, summation -1 raised to the power n plus 1 to 1 over square root of n converges. We already saw that the absolute series corresponding to this series does not converge, so there is conditional convergence. So we say the series summation -1 to -1 to n plus 1 divided by square root of n converges conditionally. This is how we check the conditional convergence or absolute convergence. Third example is -1 raised to n over into 1 over n squared plus 1. You can easily see it can be compared with 1 over n squared, and then you should be able to see that this is all conditional, absolutely convergent. The last one will be similar to the example done in the beginning of this section with the sign of n. Just follow those steps and you should be able to show the convergence of this series. Absolutely convergent. Okay, that's all for now.